We'll start this by maybe talking a little bit about the outline we're going to use for the talk this afternoon. It's really in two parts. We're talking first about the general nature of complexity and ordering it, and I'm going to pick up several parts to that. And then in the second hour, we'll look at structured planning as a use of the kind of models that we'll develop in the first section in the particular area of design and planning. So just looking briefly at this, we'll take the graph as a model, maybe go into some of the nature of graphs and relationships which are both involved in determining what a graph is. Matrix representation, pretty much to see how that you build the relationships when you're trying to test something out. Clustering is an important part of what we're after, how you make sense out of a fairly complex graph, and hierarchy, a further structuring based on hierarchical levels applied to the clustering. And then finally, multivariable relationships, which enable us to go into much more sophisticated development of links for a graph. Then in structured planning, we'll take a look at the problem as we can interpret design problems for graph use. We'll take a look at problem elements as the key pieces of this, how they can be combined or how we can sense the relationships between them. And then computer structuring, which we'll do for a design problem, the same kind of things that we talked about up here. Finally, synthesis, we'll get into discussing a little bit about how this kind of a model can actually be used by a design team in coming up with a solution. And then I'll try to put it all together briefly with some reasons for why this is useful. All right, so starting out with the graph as a model. Intuitively, we deal with complexity all of the time. There are complex issues involving just about any of the things that we do with design. We have multiple issues we have to deal with. We have problems that we talk about. In any level of complexity quickly become multivariate or multiple issues within the problems develop. Components in products or systems can quickly become very complex as we have a large number of them. Alternatives in decision making. Another typical example. All these things are essentially pieces of a large project or parts or components of a large complex activity that we might have to worry about. They're almost always examined in terms of relationships between them. If we have two or three issues, we immediately start trying to decide why or what the relationships are between these issues. Same thing about problems or components. It's in seeing the relationships between things that we develop the kind of information we need for solving problems or making decisions. And we do this graphically a lot. I'm sure everybody's seen this kind of diagram, right? Where we start talking about relationships between elements in a system diagram. What we're really doing here is identifying components or component parts and then establishing some relationship between those things or among those things by use of some form of arrow or other interactive measuring or marking technique. You also see in the process area the kind of diagrams like this, where you've got some kind of a process explained by a series of diagram types, where these tend to be tests and these tend to be actions, and you may have special ways of describing these with other forms and so on. But the same thing is true here, even though now we're not talking about things so much, but we're talking about actions and tests. We're talking about elements and relationships among them which express something fairly complex, a procedure or a process. Flow diagram, maybe, or a process diagram. And that extends to other things. Probably the most classic thing we ever see is the old hierarchy expressed in these terms for describing an organization, right? Down comes the president and he discusses, or he's in charge of the vice president's in charge of somebody else and so on. Again, a series of individual elements which are organized by some kind of relationship to give us an ordering or pattern of some kind of information. In this case, an organization chart, organizing people in a hierarchical way. Well, now, the reason I bring this up is that in every case, we're talking really about the essence of a graph here. And what have we got? We've got individual items which are connected in some way, and the connection is a relationship. So, in fact, in spite of the fact that these are quite different, we have actually a great deal of similarity in the structure or the essence of what those diagrams are. They are really graphs. And so, let's talk about more specifically what a graph is. So, I'll say graph as a model here and try to pick this up a little more specificity. First, what about a definition? A graph, very simply, is a figure made up of vertices connected by links. The key, the vertices and the links. If we go back to our diagrams here, these would be vertices, and the connections in between them would be the links. Now, graphs have lots of different properties. I'm not going to try to get into any particularly in-depth study of graphs, except to just mention a few things and then show you how we use them, particularly in the case that we're after here. For example, just a few items. They can be connected and disconnected. We should be able to actually deal with both of these in our work. A connected graph simply means one in which there are connections between, in some way, between all of the various elements or vertices, and you can get from one to another in some path of links. That would be a connected graph. However, they don't have to be like that. If I were to take away links and just have say that construction, that also is a graph, and it's a disconnected graph. In fact, we can't get from here to there is not terribly troublesome to us and the kind of thing that we need. So we can actually work with either connected or disconnected graphs. They can be complete or incomplete. We would like to be able to deal with them either way. A complete graph is one that has all the possible links that it could have. If we have 5 vertices here and they're all connected to each other, then we have a complete graph. If any one of them is missing, it's incomplete, and then a degree of incompleteness can be developed as, say, for example, a term we call link density. So that would be an incomplete graph. This would be a complete one. Another thing that we sometimes find of interest to us is whether a graph is planar or not. That's particularly interesting if you're using a graph to describe three-dimensional space. The term is planar, and the opposite would be non-planar. A planar graph is one in which all of the vertices can be put in a plane, and the links between them do not cross over each other. So this would be a planar graph. How about this one? Is that a planar graph? Yes, it is. And the reason is that in graphs, and this is another interesting thing to think about, we don't really have to deal with actual links or actual form. We're talking about rubber band lines, really, as representing these links. So I can also draw this graph like this. And the one which looks like it crosses over can be brought around like this. So that graph is the same as this graph, and it's a planar graph. It exists in one plane. It can be drawn in one plane with no crossover links. How about one like this? Draw a complete graph here for 5 vertices. What do you think about that? Is that planar or non-planar? It's non-planar. There's no way that I can draw this one without having at least some crossover. So let me just give it a try here. I can go so far like this. That's all right. Now the next one, maybe I want to draw this one, so instead of crossing over, I'll put it out here. That's okay. Now I've got to draw one more. I've got to draw this one, but I can't get from here to here without crossing over. I can do it that way, and that's no good. I can do it this way, and that's no good either way. So that is a non-planar graph. And so you'll see that. Now you could see that this would be useful perhaps in dealing with a building, and where we had to talk about relationships between rooms, being able to get there on one floor. We'd want to have a planar graph. It was going to be one floor. And finally, one other little property that might be worth mentioning, and that's graphs can be directed or non-directed. We're going to be interested in non-directed graphs here. It simply refers to whether or not there's a precedence expressed in the graph itself. If a link has meaning one way, it's not the same as it is the other way, then we have a direction implied, and usually we put an arrow on it to indicate that. So this might be a directed graph. That would be typically. In our work, we're going to be interested in relationships that aren't directed, that work either way. So you would see no arrows associated with the graph. Usually we just put lines on them to indicate that things are linked, and that's it. So looking at most of our interesting areas here, we'll find non-directed is important. Planar, non-planar depends. Connected, disconnected, we ought to be able to handle both of those. And as far as complete and incomplete, this is going to be useful to us in terms of the density that we can associate with a given graph like this. If these things are connected as heavily as are indicated in a complete graph like this, that means that they have a great deal to do with each other, and whatever terms it is that we're using. So complete to incomplete will be kind of an interesting point for us, and also the degree of incompleteness will be important. So now let's go back and take vertices and links and see what we're talking about in a general sense, because it's the use of the model to approximate things that were of interest, that we're interested in, that's important to us. So first of all, let's say the vertices, and what do we want there? These are going to be, in a general sense, things of interest. And the links will be an indication that a relationship of interest is fulfilled for two linked things. Well, that's about as general as I can put it. And I want to keep it that way because the power of this kind of a model, a graph model, is very, very good for our purposes. As long as we can keep it general, we can apply it in many, many different ways. Let's talk about what this link means and see how we can get some of the generality into the model with that. Which gets me really to the next step of our outline, which is relationships. The links are going to express relationships, and so we might as well talk about that. Relationships. What's the definition of a relation? An association or associative quality that can be tested for all pairings of a set of elements, or set of vertices. I'll use elements in here, and I suppose it's good at this point to say that we talk about a set of elements. When we talk about a graph, we're talking about vertices, but actually the elements and vertices will be, for all intents and purposes, the same. We have to deal with vertices and links in our little clusters and graphs, but the vertices will be maybe problem elements as we get further along, or they may be in some way parts of a problem, components or some of those things that we talked about earlier. In math terms, we can set up a little expression like this, which we won't belabor, but what we're saying is there's some kind of relationship R which we'll set, and it can be very general, very loose kinds of relationships, or very specific, very tight. They can be, as we'll see, of many different kinds. And we take any two of the elements in our set of things we're looking at, and we say, is it true or false? Does X have this relationship with Y? If it does, the answer is yes, there's a link in the graph. If the answer is no, they're not linked. And that's how we generate the graph. Let's take some examples of relationships we might have here. One of the ones that you're probably most familiar with is one called is greater than. And of course all the things that go along like this. There are many, many of this arithmetic nature. If I were to take all the real numbers and say, put one here and put one down there and say, is this true? That 3 is greater than 4. True or false? False, right? So no link. 4 is greater than 3. True. So there is a link in that case. So this greater than is a typical relation, and we can take a whole set of numbers and we can decide which numbers are linked to which others on the basis of this particular relation, and can use this then to get some insight into the nature of the set of numbers. We can also use things that are much less rigorous than that. I mean, we definitely know whether a number is larger or smaller than another. It's either yes or no, or if they're equal, and we can deal with that one too. But and here's another one has that kind of certainty. Is first cousin of. I can take a whole clan of people and subject them to this test. I pick up Amy and take a look at John and say, is Amy is first cousin of John, true or false? If the answer is no, there's no link. If the answer is yes, there is a link. So I can use this as an ordering relation, again, to examine a whole group of people, decide whether or not they are related, put the links into the graph. Now those are kind of general things, and I'm sure you can see the power of that. But let's get some things that get a little bit more specific, maybe to the kind of things you might use in design. How about communicates with? Now there's a very useful relationship if it turns out your problem is how to organize a group of people in an office building. Communicates may be the chief reason that you ought to put people together in a space. And if you're using one of the open office planning systems, this kind of relation is probably the one that's being used. It's being used like that in and as far as I know, just about every major systems approach to office planning, some form of communication analysis. It gets down to some version of whatever communicates with means. Here's one that, incidentally, that's not always that clear cut either. What do you mean by communications? We have to go in and pick up some special pieces, maybe divide that up into a number of things like instructs or influences or provides information for, and maybe we have to come up with a composite of communication ideas for that. Perfectly okay. How about another one? Is often bought at the same time as. Now this would be something you could do some marketing study with. Perhaps you've got a product that you're introducing in a market, and you're trying to find out, what do people buy? They go down to an electronics store and they're interested in buying one kind of product. What else do they buy? If they buy more than one thing, what are the groupings that come up? If I use this, then I'm going to begin to see relationships between products that are bought at the same time. Now, I say often bought at the same time as, so I don't even have to have a certain relationship there. I can say that is more statistical. We could say, well, often means 50% of the time or more. We could use it in that, how do we say that, statistical way, I guess we could look at it that way. So it gives us a fuzzy way of operating. Maybe that's the term we ought to use. Here's another one. Is used with. Oops. Get that off there. Is used with. Now there you might be talking about control. So you've got a fairly complex control panel that has to be developed. And it has several different procedures that have to be followed. Startup and emergency procedures and normal operating procedures for 4 or 5 different kinds of functions. And maybe we've got, say, 50 lights and switches and knobs and things to go with. The problem becomes interesting enough to apply some real analysis. This kind of relation set up on all of the various components will tell us something about those that ought to go together, perhaps in the same area in the display. And maybe even tell us something about the order that we ought to put them into. We could make this a directed relationship by saying as used before. As it is here, as used with is a non-directed relationship. A is used with B, B is used with A. Doesn't make any difference. If I say as used before, then we get a directed relationship, and A is used before B, but B is not used before A, so we can now establish procedure as far as along with everything else. All right, so you get some of that hope, some of the flexibility and breadth possible with using relations. You can, if you find the right thing that makes sense for your analysis of the problem you're working with, and then you apply that to the whole set of things that you're looking at, and develop a graph which now provides a model for us. Now, what we're talking about here is this is a set of knobs or a set of switches and things, and for convenience sake, I just show them as a series of points. But there, that one's used with that one, and that one's used with that one, and that one's used with that one, and maybe this is what we get as a graph. And what we're seeing now is a cluster, which we'll be getting into in a minute, of things which are used together and probably ought to be in the same place, and another cluster, which again are used together, and there's some commonality there. At least one of the components is used in both sets of operations. We can just give you a couple of insights on applying this kind of thing, what can happen. And we've done a lot of things over the years that have been sort of whimsical and inventive in applying relations to just get people used to thinking about that. And I've always thought one of the ones that I liked most was a relation was set up by one of the students who was a gourmet cook. And the relation was complements the tastes of. Now, if you were to take a whole set of gourmet foods, and frankly, when he did this in the class, I found that I really only knew about maybe a fourth of the foods that he had put on there, and these were gourmet dishes. Now, if you test them with this kind of relationship, what do? You know, you're building clusters of foods that go together. And so what you expect happens, does indeed. You get clusters of foods that go together and make a meal. And as you see this, you see these other things developing, other clusters, and you can, if you look at them carefully, you know what you're talking about. You can begin to put names on these as to where they might come. What actually happened when we ran this test is we found that we were identifying some very interesting meals. The meals went together at higher levels, and as we clustered the clusters and sort of saw that these things kind of went together, and maybe there's some more over here, we could identify Northern European meals coming out, and Asian or Middle European meals, and that kind of thing. We actually could put an organization on the foods based on how they taste. Rather intriguing idea. Another thing we did, which I thought was interesting this way too, is look at fish and shellfish as a problem of association, where we're trying to organize them not on the basis of their biological features, but on the basis of how you cook them and how they taste. Because we have a real problem in the United States, so we've got a large number of cuts of meat that are produced, and people really understand those rather well. But when you get into fish and shellfish, most Americans really don't know too much about fish. They recognize a certain few. You get ocean perch and you get scrod. I think they know what that is, and tuna and some of the other salmon and fresh fish for those who are in the Midwest, and ocean fish for those who are on the coast. But when it gets right down to it, the number of fish they can identify and actually be able to use in cooking is really rather small compared to what's available out there. And we're putting a lot of pressure on certain species of fish because of that. And there's a concentrated effort by the maritime community to widen out the consumer's understanding of fish and types and all. And so what we did a study based on this technique to organize fish on their culinary features rather than their biological features. Intriguing way to be able to do these things. Well, let's talk about how this all goes together. I think the matrix representation, I believe, is next, and it's appropriate we talk about that right now, because once you set this up, what you're really doing is inventing a question, if you will, which has to be asked of every pairing of elements in the set you're looking at. And if the elements are foods or whether they're fish or whatever, we need some way of getting the information down. So the matrix turns out to be a delightful technique for doing that. We don't really have to do that if we're using a computer to operate it, but visually it makes good sense. And a lot of times when you're working with relatively small problems, it's easy enough to set it up that way. When we take a matrix, what we're really doing is taking a device which can diagrammatically express all the possible interrelationships, or I'm sorry, for any relationship, express the yes-no quality for all the pairings of a set of elements. So let's say we had here a set of elements which represent a group of people in an office. So here's John, and here's Tom, and Mary, and Ed, and Ray, let's say. And then if it's a square matrix, in this case, we're also going to use it to compare the things against themselves, so I'll put them across the top too. So here's John, and Tom, and Mary, and Ed, and Ray again. Now, because I've set it up this way, I have every possible every possible comparison here for me. I'm not going to have anything on the center diagonal, because talking about John against John usually doesn't mean anything. There's something that sometimes things we could do with that in relations, but in the one I'm going to work with here, that won't be meaningful. Let's set it up as communicates with, because that's an easy one to think about. So we go through, and by interviewing or developing a questionnaire or something, we come up with a decision as to who communicates with whom. So now what we do is we fill out our matrix, and let's say we have John communicates with Tom, and John communicates with Ed. Tom, we find out, communicates with Ann, or what have I got here, with Ed, and Mary communicates with Ed and Ray, and Ed communicates with everybody, and Ray communicates with Mary and Ed, and we've got ourselves a representation of all of those communication links that exist. Now that is equivalent to the graph. It's just easier to establish the information this way than it is to draw it up as a graph in the beginning. Because what you do, and this is where using a matrix like this has some real value, you you go through and you take John first, and you talk about everybody, Tom, Mary, Ed, and Ray, and establish yes, no on each one of those cases. Then you take Tom, and you go through and everybody again, and Mary, and Ed, and Ray. And what have you done? You've made you've made the decision twice. So you've got to check for yourself, because this matrix is symmetrical around this diagonal. And that brings up the second thing that's of value in using this. It should be symmetrical in a case like communicates with. This is a non-directed relationship. It's the same if Ed communicates with Tom as if Tom communicates with Ed. So we ought to be able to look at this diagonal as a symmetry line, kind of turn the head, and it should be the same here as it is on the other side. Is it? No, it isn't, is it? So what did I do? I missed John and Tom, right? Here, if John communicates with Tom, then Tom should communicate with John, so I should have that in there. Are there any other asymmetries in there? No. So that's a test it provides. Now, if you were talking about a directed relationship, then it would always be show up on one side and not on the other side. So it would be totally what they call anti-symmetrical. And you can use the same kind of symmetry check to see whether or not you got it all down. So the matrix representation, while it isn't always necessary when you're working with a computer, expresses what we're talking about, expresses the relationship between things, provides the form that we need to work with. Okay, let me put them down a couple of these things. It's a convenient notation form. I go into it because you may very well want to work on this level with some simple, quick analyses. It sets out all the decisions that have to be made. There's a spot in there for you to put a yes or no for every possible decision you have to deal with. And finally, it's self-checking, as we just mentioned. So some good points for that. If I were to take this now and turn it into a graph, what I would do is pick our 5 people here and set them up as vertices, and then put the links in that are expressed by the spots on the matrix. So here's John. Oops, spell John right. John, and let's see, what do we got? John, Tom, Ed, or John, Tom, Mary, Ed, and Ray. I've usually just put them around in a circle because you don't really know what you're going to get until you put the links down anyway, so it's just as good as any form. So John is connected to Tom, means he communicates with him, and with Ed and Ray. Or we just Ed, Ray, sorry. So we got 2 links there. Tom is, well, this gives me the double check. Tom is connected to John, right? He's also connected to Ed. Mary connected to Ed and Ray. Ed and Ray. Ed is connected to everybody. We've already got 3 of them. Here's the 4th. And Ray is connected to Mary and Ray, and that should be both in there, and there they are. Now, to make it a little more understandable, you try to unwrap these things and try to make it a planar graph if you can, because that's the easiest way to see it. So I can see here that I could take Mary and Ray and kind of pull them down here and unwrap the thing a little bit. That would make it easier to look at, understand. So here's John, and let's see, I've got John and Tom and Ed, Tom and Ed, and they're all linked. And then I've got Ed with Mary and Ray off the side. So here's Mary, whoops, Mary and Ray, and they're all linked. So I can see that really I've got one communication group here and another communication group here, and sort of with Ed serving as a hub, some kind of important communication function probably. So the point of all this is they're equivalent ideas, but one's easier to use to set up the information and one's easier to use to see the relationships. The graph is really better for seeing the relationships. Okay, next point will be clustering. Let's see what we can do with that. We have computer programs that will work on these things. There are a number of different kinds of computer programs around that deal with clustering. We're going to talk about one here particularly called VTCon. I'll get into that in a minute. But first, let's just talk about why we have to do this. This is actually pretty straightforward. You can see how the clusters work out, and it's no great leap of faith to think that you could turn that into useful information. Problem is that if you get a lot of these things, a lot of Johns and Toms and Marys, and a lot of links between them, you really can't unwrap it that easily. You can't really see where that structure is. For example, let's say, and I'll just skip the people here, and you go back to the abstraction. Well, let's say I have 10 elements, and this is the way they turn out to be represented in the graph form. Nice geometric thing. If I asked you to tell me where the clusters are, you wouldn't have much problem, right? Here's a cluster, right? Here's a cluster, and here's a cluster. Real easy. No trouble at all. And that is useful to us because, of course, the clustering now gives us one level up of structuring. Before we had 10 things, now we know we've got 3 groups of 4 things, which lets us deal with it in a lot easier fashion. That's the old Miller's number plus magic number 7 plus or minus 3. We can't handle too many things in the mind at one time. We can handle groups of 3 things very nicely, and within that we can handle 4 things very nicely too. But when you start trying to deal with 10 things and just remember relationships among them, it's really difficult to do. So, all right, 10 things, no problem. We should be able to handle that. Let me show you another one. Here, I'll put some letters on this just so that we can keep them straight. Here's A, let's see, B, C, D, E, F, G, let's see, H, I guess fit right in there. So that's 10. 10 things again. Now I'm going to put the links in them into this little graph. So A is connected to C, and to F, and to H, and to J. Let's see, how many is that? 1, 2, 3, 4. And to B, 5. Okay, B is connected to D, and to E, and to G, and to I. It was already connected to A, and I'll just pick up the new ones as we go along here. C is connected to F, and to H, and to J, as well as to A. And D is connected to E, to G, to I, and I think that's it for that. 4 on there, right? E is connected to G and to I, in addition to the ones it's already connected to. F is connected to J and to H, as well as what it's already connected to. And G is connected to I and its other things. H is connected to J, along with the other things. Now, you tell me, what's the clustering? 10 things, just like the others. But now all I've done is I've just put them down and told you what relationships existed. I didn't tell you anything about, I didn't do any organizing for you. What I've done is tell you the kind of thing that you'd get if you went out and took a questionnaire and applied it. Well, it turns out that, in fact, this is just as amenable to this kind of clustering as the original one was that I did up here. It's just a matter of having it organized right so you can see it. Let me draw it another way. Here is E and G, I, B and D, A, C, F, H, and J. And if I put the same links in there that are in this one, this is where they fall. And the obvious clustering is simply breaking that AB link. Now, the trick is that I've got to have it laid out. if it's all laid out correctly, we see the clusters. But the problem is, well, how do you get from this to this? See, now if I actually insisted that you go through this, you'd spend enough time, you'd start looking through here, and you begin to kind of look at one or two of these, move around, pick up some other things, and trial and error, beginning to develop what you thought were clusters, and eventually you'd see it. You'd see the same thing. But wait a minute, I've only got 10 here. 10, that's scarcely worth bothering with as a problem. And most complex problems, we're going to need about, we're going to find maybe 50, 60, 100, 150, 200 different components that we need to work with. Then trying to do something like that by eye is really impossible. And so the program that I'm going to talk about here, which we're going to use to get these kinds of clusters, is going to try to, and I say try kind of advisedly because it's not a program which is an absolute program. There's no guarantee that it will actually find everything. It almost always finds everything useful. But because of the problems associated with looking at all possible arrangements, it's impossible to actually prove that you can get every way. Maybe they'll prove it, but you can't do it in any kind of real time. Let me just point out that I think what it's really, it boggles the mind to think about it, but if I have 50 vertices with links in between, and I set up an algorithm which will look at every possible cluster. I say possible cluster, it means I say A and B. Could that be a cluster? A, B, and C. Could that be a cluster? Go through and check these out. And I allow 1 microsecond to make up a cluster and test it and decide whether it's useful or not. How long do you think it would take to deal with 50 vertices? It's one of those things that you cannot intuitively grasp. The answer is it would take longer than the universe has existed. And it just doesn't seem right, but that's what it is if you go through the combinatorial arithmetic on this and figure it out. So we can't come up with a scheme which is going to be an absolutist scheme which will work. In fact, what we've got is a program that works heuristically. Some good ideas and some good directions to try, and it almost always finds what we want to find. But let me try to at least explain a little bit about this. I'm not going to go into this program in great depth, but just a few things to give you some idea. First, what it's going to do is it's going to take advantage of what the human eye can do well. The human eye, can you read that? Is that reasonable? The human eye works well if, first, the problem is well arranged, or what should I say, the graph is well arranged. We didn't have any trouble in spotting the obvious clusters as long as they were well arranged. These cases were fine, that case was not. It's not well arranged. The other thing that we can do with the old human perception system is find this kind of clustering if the problem or the graph is small. Because we can kind of make some changes and move things around in our minds. For example, if I have a thing like this, A, B, C, D, and it's linked up like this, it doesn't take a major step to unfold it like we did before so that you get an A-B connection with a C here, and then we just unwrap this D part of it and put it over here. Now we see that that's a better arranged structure, and we make our decision that those are the two clusters there. So that's fine, because the reason we do this is that we're taking advantage of our ability to order things. So the VTCon program, which is the one we're talking about now that will do clustering for us, takes advantage of these properties of the human system, or should I say better, it looks for analogies to these kinds of properties. I suppose I better say what VTCon stands for here. It comes from, was started out back in 1966 as a program which was used to produce hierarchies from given input sets like we're talking about, or clusters like we're talking about. And so at that time it was titled variable threshold condensation. And that's just a little nice piece of trivia to tack onto things that you've got. It uses that in generating hierarchy, which we'll get back to in a little bit. But as far as doing the clustering we're talking about now, that was added in later on. We just kept the name of the program, VTCon, as the because it had been passed around a fair amount. Now what it's doing to deal with our clustering here is it's abstracting, or I'll say it abstracts the human qualities of one, cluster recognition. We can see them if they're well arranged. So we're going to try to find some way here to, lots of big quotes, see a cluster when it shows up. And second, the other thing that the human perception system does well, we're going to use order of search. Try to find a way, not directly simulate, but take the idea that in a human being we tend to look at one thing and then follow it to the next and follow, and make tests go back and sort of like maze threading to find the best set of connections. We can do that for a little while. It's again Miller's magic number problem, but we're going to try to pick up on those two things. And the way we're going to do it, the way the VTCon program does it, is it sets up some basic mechanisms. And these are, first, structural link weights. And second, vertex weights. Now, as I said before, I'm not going to get into this in depth, but just a little bit may give you enough of a smattering to make it feel a little better as a technique. So first, let me say a little bit about what a link weight is, and then vertex weights. A link weight is defined as the number of three-link circuits a link appears in. So, for example, here is a link between two vertices. How many three-link circuits would that appear in? Well, there aren't any three-link circuits, so the answer to that is 0. It doesn't have any weight at all. Now add 1 to it here, and now I got 3 vertices, and I have links between each pairing, and so that is 1 three-link circuit, and so the link weight for that particular link is 1 because it appears in one three-link circuit, and the same is true for the others. If I go up 1, again using complete graphs here, so you can see that now I take this link, say where is it? It appears in this circuit and that circuit, so it's a 2. And if I take each one of these, we'll find that they're all 2s. So that's a link weight of 2 for each one of those, and you can continue that on up. Curiously, well, you might not think it would be as you go like this with complete graphs, just continuing on up one vertex after another. It might not be obvious, but here you get a 3, and that's the same for all of these. It'll be 4 if you go to 6. So I'm probably missing a few in here, but you can see, take the bottom one, you can see it's in this triangle, and that triangle, and that triangle, so it gets a link weight of 3. So that's what the link weight is. Second thing is the vertex weight. Incidentally, the reason we're going to use that link weight is to help us recognize that this particular vertex belongs with those 4. It's kind of like magnetic or molecular attraction. You can think of that as another analogy that's really being employed here. Now the vertex weight is the sum of the 3-link I'm sorry, sum of the weights, get that straight, of links incident on a vertex. That just means the links that meet at a vertex. Incident on is just a term that's used in graph theory, divided by the number of links incident on the vertex. So if I were trying to figure one that was, say, reasonably complex here for just a little example, let's put together a fairly messy little graph here. And the question is, what would be the vertex weight of the one here in the center? Well, in order to get that, you have to do the link weights first, so we'll do that. If I take this one, these are all in one triangle, so that's a 1, a 1, and a 1. And this is the one we saw up here, so these are 2s, 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 and so on out here. Let's see. And then this is like this one was a 0. So to figure this vertex weight, I take the sum of the link weights. That would be 1 plus 1 plus 2 plus 2 plus 2 plus 0, which is what, 2, 4, 6, 8. And I'll put that in there. That's 8 divided by the number of links, which is 1, 2, 3, 4, 5, 6. So that's 1 and 2, 6, or 1 1/3, right? And so that's how we figure vertex weights. Out here, this would be 1.0, 1.0, because they're 2 divided by 2. This is 2, 4, 6 divided by 3, or 2.0, and so on. So you get the idea. So that's the basic technique. That's those are the mechanisms that we use in developing this program. Now, actually, the program is considerably more sophisticated than that, but it uses this kind of an idea as the starting way to get information about the graph structure. What it does is it then breaks these things down by using this order and weight business to kind of accrete clusters from individual vertexes or vertices. So I'll say that it finds clusters by accretion. And then I'll show you a little simplified example with an understanding that it goes much farther than this, but this is kind of the way it starts out. Let's see, well, let me put some letters on this. Here's A, B, C, D, and E. And I'll put F and G up here. And I'll put H, I, and J down here. And link them up like this in sort of familiar pieces that look sort of like, and you're right, complete graphs. So we call them complete subgraphs here because they're part of a larger graph. And see how our little system would operate to decompose this thing. That's the term we use, to decompose the graph into clusters. Ideally, what it should see would be this one, this one, and this one. And the way it goes is that we first do this link weight business, and we now know that these will all be 3s, which is probably the reason my best reason for using this, just to save time in thinking about all those triangles they get into. These will all be 1s, and these will all be 2s. We got all our link weights in. The next step is do the vertex weighting. And this will come out to be 3. And this will be 3, 3, 3. And these we know will be 2s. And these we know will be 1s. Of course, I'm cheating and saving the tough one for last. But now, let's see what this one is. That's 3, 6, 9, 12, 14, 16, 18, 19, 20. So it's 20 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, which is, according to my notes, 2.22. All right, so that's this one in here. Now, what we do is we take these things and put them in order, and then watch this accretion process work. So this ordering business, as I said, comes in here, and we use the vertex weight as the ordering mechanism. So let's just start with the highest, and that's A, B, C, D. They're all the same. So I'll say order A, B, C, D, and they're all 3.0s. Then our next one down is this 2.2, or 2.22. That's E, and only one of those, and we've got some 2s over here. That's Hij at the 2 level, and then F and G at the 1 level. So we take them now in order, and we just test out and see that we can add things to it. I'm going to make this a simple requirement. I'm just going to say that we can't form any subgraph or any cluster unless everything that goes into it's connected to everything else. In other words, unless it's a complete graph. And of course we know that we're going to find 3 of them, or we should. So what happens in the program is something like this. It starts out with A, and then it checks B against that to see if it's connected to it, and if it is, it puts it in. In this case, we know that B is connected to A, so it goes in. Same thing with C now, and you can see how the order thing is going to work. It goes in again. D also is connected to all of these, so it goes in. E connected to all of them, so it goes in. And we have just agglomerated or accreted a cluster here. Now we keep on going down the list, so now we're at H, and we say, can H go with all of those things? Well, you back and you find out what's linked to what, and you see, no, it's only linked to E. So it starts a new cluster. Then I, and I won't connect to all these, but it will connect to H, so it goes in with H. And J, same thing. It'll connect to I and J, but not these others, so it goes in here. Now we're down to F. Same thing happens. It's only connected to E out of what's up there so far, so it starts a new one. And G was connected to F, and so we've got that much. Now the program goes back and loops through again to see what else, see if it can do any more, see if it can add anything in. So I'll just draw a line here. It says the end of the first pass, and we'll go through another quick pass. We'd say A, it's already in there. Can it go in here? A to Hij? No, it's up here. All this stuff's down here. How about B? It's in there. Oh, I'm sorry. H also. A we also check down here, and we can't add it because there's no linking over here. So we go on B, C, and D, and then the same thing happen. When we get to E, we'll see it's already in here, but we'll see now that it could also connect to all of these. Now, we couldn't put it in before because there wasn't any graph at that point when we put it in here. This is all we had. But now we can add it in. So we add it in, I'll put it out here. And the same thing down here. So what in fact is we've done is we've recognized these clusters. And of course we go through and check it all, but nothing more will come out of it. So that's the clustering that the program will pick up. Now that's admittedly a simple case. I'm ignoring a whole lot of heuristics that come into play when these graphs get more complicated and certain special things happen to them that would tend to make this simple scheme not quite work. And so that's all built into the program. But the idea of accretion and this kind of clustering is the basic technique employed. All right, so next step is hierarchy. How am I doing for time here? Am I okay for time? Can I get, all right, we'll just, I think I can make this in another few minutes. Maybe we can stay with our first, we'll be close to the first hour on our tape. All right, so hierarchy. Why do we need it? Well, if we don't have hierarchy, what happens if we have a lot of clusters? What if I have 75 clusters? I'm right back in the same place I was if I had 75 elements or vertices and a lot of messy connections. I can't see any pattern. So a way to handle that is to cluster the clusters. And that is building up a hierarchy. So that's really what we're doing with hierarchy. It's just an extension of the clustering idea. Now, instead of clustering at the lowest level, where we are dealing with the graph directly, we're going to be dealing now with these things as the entities and trying to cluster them. So let me give you a fast pass through here, and I'll just show you sort of what this is all about. Let me make a graph that I can easily decompose and show you visually what this clustering would be like. Here's a set of elements of some kind. We'll call them just by numbers, 1, 2, 3, 4. I'll put some more out here, 5, 6, and 7, and 8 and 9, and 10. I'll sneak out over here. And then I'll come down here and put in 11 and 12, 13. Of course, I'm being very orderly about this because we really want to see this one. And normally when you establish these relationships, of course, you do not know all this nice pattern. You're not going to find that till you run the program and develop the clustering in the hierarchy. So I've got 14, 15, 16, 17, 18, and 19 down here, and I'll make that into a nice, very obvious set of clusters. And now to make this whole thing a little more complex, I'll put in some cross-linking. 2 to 5, 4 to 6, 6 to 14, and let's see, 7 to 15. How's that? I guess that'll work out pretty well. And 3 to 11, and 4 to 12. So we've got a connected graph now. Everything you can get everywhere by some connection of paths. Now, if we were to run our clustering algorithm on this, you can guess what we might find. We'd find, now I'll put some numbers on these in order to keep track of them, because I'll convert this in a minute to another form. But let's say this cluster, which certainly exists, we call 101, meaning level 1, cluster 1. Now, there's another one over here. That's pretty obvious too. So I'll call that 102. And 103 will be this one here, 7, 9, and 8. And 104 will be 8, 9, and 10. And I'll come down below, do 105 down here, 11, 12, and 13. 106 will be the next one in line here.